Welcome to Spring LIB.
Now in this question, we are given the potential, right? The potential that a particle is experiencing, which is given over here, and also the wave function of the particle. So we're only interested in the length between negative L and positive L, right? In this region where we have this potential. We want to find what is the energy, right? The expression for the energy of this particle within this region. And the way that we will do that is by using the Schrodinger's equation. Right, what we want to do is we want to substitute in psi as well as the potential, and we should be able to extract out what is the energy E. So the way that we're going to do that is, first of all, we need to find the second derivative of our wave function, right, to put it into here. So we differentiate our wave function once first. And then we differentiate it again. So this is what we'll substitute into the Schrodinger's equation. So putting everything into the Schrodinger's equation. This is for the first term. For the second term, with the potential, it's negative h bar square x square over ml square minus x square multiplied by the wave function, which is a 1 minus x square over l square. Now if you're quick to notice, you should be able to see that, right, if we factorize out l square from the denominator, right, in this bracket, if we just divide by l square and we factorize the l square out to the outside of the bracket, we will get 1 minus x square over l square, which we can cancel out with the numerator. So simplifying this a lot, what we get is h bar square times a over m times l square. Sorry, this is l square minus away h bar square times a times x square divided by ml to the power of 4. And we equate this to the right hand side, which is just the unknown energy multiplied by the wave function. Now again, if you're quick, you should be able to see that there is quite a few common factors on the left hand side of the expression, and the common factor would be h bar square a ml square. So if we were just to factorize that out, this would be h bar square a ml square. What we get left is 1 minus x square over l square, which is pretty familiar to the right hand side. You can see that we have this 1 minus x square over l square term. We have this constant a term, the normalization constant, and therefore we can infer that our energy would be just h bar square over ml square. Now we can move on to find what is the normalization constant. Now the normalization constant would help us to actually ensure the total probability of finding this particle anywhere to be 1. Right, so we are given that, right, a normalized wave function is when we integrate the wave function throughout all space from 0 to infinity, right? The probability density function, which is the square of the wave function, this will give us the total probability. Sorry, this is not 0, this should be negative infinity to infinity. This will give us the total probability, and this must be equals to 1. Now in our case, because we are given that the wave function is 0, right, beyond negative L as well as beyond positive L, so we are only confined within negative L and L, right? So for the rest, the integral will just go to 0, right? So we don't have to bother about them. Just have to bother about the wave function when it is within L minus L and positive L. So the wave function squared would be a square 1 minus x squared over L squared squared. Right, so we have to integrate this, and we must equate this to 1. So it'd be good if you can just open up the brackets, right? And then we can integrate the terms one by one. Now substituting in the limits from negative L to positive L. Right, so when you substitute in negative L, you will minus all the terms. So minus negative L would be just plus L x cubed. This will be negative L cubed. So minus negative L cubed. So it's still a minus. This gives us a square 16 over 15L. And since this is equals to 1, we can infer that A is equals to square root of 15 over 16L. Right, so this is our normalization constant. Now to determine the probability for the particle to be found between minus L over 3 and L over 3, again we use the probability density function. We need to integrate the probability density function, which is just psi square from negative L over 3 to L over 3. So we have to integrate this function again, which we already solved for. Right, so a squared, we will substitute in the value for a, which we have already found previously. This is just 15 over 16L. And the integral inside is just x minus 2/3 x cubed over L square plus x to the power 5 divided by 5L 5L4. Alright, but in this case the limits of the integral is minus L over 3 to L over 3. Right, substituting in, you get something like 3 minus 2L over 81 plus L over 1215 plus the same thing and what we get is actually just 47 over 81. Right, the L will cancel out, which is around 0.58.